The lower reservoir here is the yellow one in this picture. And the upper reservoir number 1, the lower one, is in yellow. And here's where you mapped out between the discovery well and well 1009. And then the green up there is the upper reservoir. And then that third horizon, that Maya Seneca that we had found from the fossils, also correlated that across too. So it was pretty easy to do from the discovery well to well 1009. I put in a few more faults. A little bit trickier to do between 1009 and well 1A, but we did find the reservoir, the green one. The yellow one, well, maybe it's there. It's a question mark. Not 100% sure, because that gets in a kind of a structurally complex area where your reflectors are all kind of mixed up and everything. Remember too that we did that this seismic line is not a straight line, but it's a loop. Okay, so you can see down, if you look in the lower left corner, you see in black is the outline of this seismic line, and it's a loop. So what you're looking at is part of the same structure. The same structure here is the same structure over there, more or less. And so this yellow area in our yellow area here in, that's not showing up, oh, there. The yellow area in there is part of the same structure, an anticlinal structure that's faulted, okay? So you want to keep that in mind as well. So we took that back to PMEX, and they said, wow, that's great. Okay, now can you now go and now that you've correlated on the seismic, you've opened up some new areas for looking at drillable prospects. So for example, the area in yellow here, okay, you've got one well there and another well over here. How about in between? Is any of this, it's the same reservoir interval, is a transgressive sand, it's probably a transgressive sand all the way across here. So can you go and look at the wells, retest the well, or we told them, go and retest the wells. What we'll do is we'll go through all the well logs in the area, and there were many more, and what we'll do is we'll highlight what we think might be reservoir sands in those two intervals, and you go ahead and test them if you think they're correct. So here's just an example of what we did. Wherever we found a well that we could tie to the seismic, those two reservoirs, and for example, in this well, we didn't see anything, in this well here, we didn't see anything too prospective. This was the interval. We were able to find the two reservoirs intervals, but they, and they're still kind of blocky or coarsening up or finding upward pattern, but we didn't see any gas, any indication of gas accumulation. But we went to another well, or excuse me, another interval in the same well, and we got these high resistivity kicks, and we said these are two intervals here and a third one down here that you want to test. They have the blocky log patterns and the finding upward log patterns, and they correlate with the reservoir interval on the seismic. So this well these intervals are the ones you want to test. So we went around and did that for a whole series of wells, and we had success. We found a number of sands that had all the characteristics in the discovery well within the two seismic horizons that marked the reservoirs. And so we made a list that these would be the intervals that you would want to test in some of these wells that had never been tested because they were wells just drilling down to the Cantarell field. So it was a success story. Well, there's another nice ending to this story as well. We back up. Very happy, it was a success story. Both of the students got their master's degree. And again, this was work done by two of my Colombian students. And the other part of that was that during the course of the study, they became very close, and they ended up getting married. And see, he's got his black hair again. Okay? It was great that first time. It turned black again. And here they are now a couple years later. And actually they have another child now too. So both geologists, both work for Occidental in Houston, Texas. So it was a very successful story. Now let me make a kind of a general point here. This kind of came up during discussion during the break time, that we could have never done any correlations if we had just used the well logs by themselves, or the well logs with the seismic. We had to have some sort of marker horizon that we could trace across the faults. Okay, and what was it that gave us that data? It was the paleontology. And whenever I do a project with a company or something, and they'll send me the data, and the very first thing I look for is the paleontology report. And the hardest thing to find is the paleontology report, because it's a very underutilized, and here you see it led to success in this particular case. It was the paleontology that gave us that allowed us to correlate those horizons and to identify them. So I'll phone up, I'll get a data package, and there'll be seismic and logs and all that, and hardly ever do you get the paleo report. So I'll phone up and I'll say to the company, do you have a paleo report? And they say, well, I don't know, I think we did the paleo, but I'm not sure, and if we did, I don't know where it would be. And so that's often the response you get. So my recommendation to you, and I saw one example during the break time that's very similar to this, that if you've got access to the paleo, always use that paleontology. If you don't have access to paleo, well, and you do have cuttings, you don't need core. If you have cuttings, you can do the paleo with the cuttings, and you should be trying to convince your manager that they ought to spend the money to do the paleontology. In this case, it worked out very well. They tested the intervals that we recommended, and most of them were gas productive, and so they were able to improve their gas production. Now, the final thing with this story is that once we had located prospective sands and they had been tested as to having gas in them, the PMEX had brought up another question, and they said, well, we've got two choices now what we can do with this new gas. We can either sell it and make up some of the money we're losing by the decline of the Cantarell field, or we can re-inject it and try to pump up the pressure in the Cantarell field, re-inject it down deeper into the Cantarell. And so that was a decision. We didn't have anything to do with that decision, but that was a decision made by the company, and what they decided to do was re-inject the gas to pressure up the Cantarell field. And so and I don't know how they did that or anything like that, but that's what happened in this particular study that we did. So it was successful from PMEC's point of view. My students got their degrees, they got married, and all of that. I got gray hair out of it myself. Okay, well, that's an example of what I've been talking about, these transgressive shoreline type sands. What I want to talk about now is the other type of shoreline sands, the regressive or the progradational ones. So here's this diagram that I showed yesterday that shows a shoreline zone with all the different transgressive sands that can occur. And then down here, a progradational or regressive shoreline and all the different types of sand bodies that you can find on that particular case, more progradational type sand bodies. In fact, many of the major deltas of the world they're progradational deltas, and they occur during high phases of sea level or high stands of sea level. But I'll get into that later today, this afternoon. So let's look now at some of the progradational shorelines deposits. And this is a very old diagram. I think it was first reproduced about 1950 or something, but it's still quite accurate. And it shows different types of end-member deltas on a triangular diagram, where you have what we call river-dominated deltas up there, what we would call wave-dominated deltas by ocean waves down at this triangle, and then tide-dominated deltas shown by that part of the triangle. And then you got a bunch that are kind of mixed, partially river, partially wave, partially tide-dominated, and so on. The reason why you get these different types of deltas is, I want to go back a second here. The reason that you have these different types of delta is, once again, it's all a function of the depositional environment, the original depositional environment. If you have an environment something like this, where you've got a river coming in, Stephen, let me back up. If you've got kind of a sheltered shoreline, that's where there's no wave action, no tidal action. That's when when your river dominates deltaic sedimentation. So you have a river coming in bringing delta sediment, okay, to the shoreline and nearshore area. If you've got a river that's coming in and depositing sediment in an area where you get a lot of wave action, that sand tends to spread out laterally in the direction of the breaking waves, so you get a different type of delta with a different geometry. You call that a wave-dominated delta. And then if we've got an embayment down here, like you see in this cartoon, where you've got tidal currents coming in and out, and usually when you get an embayment like this, the narrower the embayment, the stronger the tide. So in that case, because your tides are going in and out, you get sand bodies that are elongate in the direction of the tides. Whereas here, we're at right angles, in this one here, the wave dominated, we're at more or less right angles to the wave action. Here, our sediment that's brought into the delta, the sand bodies become parallel to the direction of the tidal currents. So you end up with these different types of deltas. And it's really critical if you're trying to develop or characterize a delta, it's really critical that you know what type of delta you have, because they're gonna have different geometries. And if I come to you and I say, what are you working on these days? And you say a delta deposit, a delta reservoir. And I ask you, what kind of delta? And you look at me kind of funny, you know, and say, well, a delta. You know, well, that's not good enough. You got to know what type, and that's one of the points I want to make here by showing you the different geometries of these different types of deltas. So let's look first at a river-dominated delta system, where the river brings in sediment to the shoreline, but there's no wave or tidal currents, or very little, so that you have the dominant sediment process is just dumping of the delta material onto the delta at the shoreline. And with time, that whole system will prograde in a seaward direction. As you deposit more and more sediment, you outbuild or prograde the delta. Well, here's a diagram, kind of a schematic diagram of what the different types of environments that might occur in a river-dominated delta. So here we have river-dominated delta. These are a couple of examples. Aerial photograph. This is a satellite photograph up here. And what it shows, this is an infrared photograph, so the pink here is actually sediment that is coming down the river. The river is here, reaching the shoreline, and that sediment spreads out across the top of the water column, the marine water, and eventually the sediment will settle out to the seafloor, and given enough time, enough geologic time, that whole system will build up and it'll build out, it'll prograde out. Well, there's different sub-environments of the delta, and we can break them out by name, and we call them delta plain, very flat part of the delta, the front part of the delta that tends to be a little bit inclined, and then what we call the pro-delta, which is also kind of an inclined surface. If we were to draw a cross well, let me back up. The distribution of sand is very irregular in this sort of an environment. You get sand in the channel. You can get some sand in the channel. And sand also piles up at the mouths of these rivers. We call these river distributary rivers. And so you get sand piling up down here, down there, showing up, and over here. And so at the mouths of the rivers is where you're going to get sand. So if I were to draw a cross-section now, across one of these one of the bodies like this, we would find dominantly mud. That's what's shown in the orange here. And then your sand would be kind of a elongate sand body, kind of like the shape of either the river or the pile of sand at the mouth of the river. So your sands are very restricted and widely spaced in this sort of an environment. Now here's a real delta of sorts that is in an old abandoned quarry in Oklahoma that I take people out to look at, because I turn this into an analog for a marine delta, even though this is just fresh water in a quarry. And I say, let's pretend that this is the marine environment. Okay, so that's the ocean. And here's the river bringing in water and sediment to the ocean. And then here's the delta. Okay, so there's the delta. And what we can see from this, well, first of all, you can see that the delta is fully exposed. It's very nicely exposed. So you can see the delta. This would be analogous to when you have a low stand of sea level, so that your delta becomes subaerially exposed. So that would be the analogy here during a low stand. What's going to happen during low stand time up in the delta environment is the dominant process will be erosion. In other words, the river now will be pretty active, and it cuts away the delta. It reworks the delta sediment, deposits it out into the ocean. So that's one process that goes on during a low stand when you have your delta subaerially exposed. The second process is what we call slumping, where you see big blocks of the delta become unstable because they're on a slope like that, and so they'll fall down and into the marine environment and be deposited on the seafloor. So during a low stand of sea level, those are the two dominant processes that go on. Well, when does it, if these are erosive processes, when does the actual delta form? When is it deposited? Well, it's deposited during the high stand of sea level, where you've got space between the sea surface and the sea floor. And so sediment coming in by the river during the high stand of sea level will be deposited there. So this was a picture that I took one summer. This was a picture I took one summer when and this really the level here of the quarry, the water here, is actually the top of the water table. If I came back in the winter time, where there's a lot of rain, I wouldn't see the delta at all. The water level would rise, and that would be the time at which you would be depositing sediment. Then the next summer comes along, you drop the water level, and you erode. Next winter comes along, high stand of the water, so you deposit. So that's the analogy, a modern day analogy to what goes on over intervals of geological time. And that is why what I said is the deltas often, most of the world's very large deltas are formed during these high stands of sea level, not during low stands of sea level, although you can get small deltas forming that way. Okay, so here is a cartoon again of these different environments and where the sand is located in a delta. The sand is in yellow. It's called bar finger sand here. And then you have sand, you can have some sand on the riverbed as well. But most of the sand accumulates as these bar fingers or another word for them, distributary mouth bars. That's another word, that's a more common word than bar finger. This picture was made in 1961, and once again, it's still a valid picture for river-dominated deltas. So what was called a bar finger in 1961, we would now refer to as a distributary mouth bar. And you can see it like in this outcrop. Here's the base of that bar, and now it's starting to come back up again. So this is going to be your sandy part here. Notice that the depositional environment is one where between sand bodies you have estuaries and bays and lagoons, very shallow water, but an environment that is mainly depositing mud. It's a relatively low energy environment. Yeah.
What about the leaf?
Levees?
Leaf.
Leaves. Spell.
L-E-E-V-E.
Yeah, well, I pronounce it levee. Yeah. Those occur, well, I showed you a picture yesterday on the river. The levees occur on the banks of the river, and they occur during flood when the river overtops its bank, and all the sediment then gets deposited outside of the channel, basically along both channel walls. Those are the levees, yeah. And they're generally pretty muddy, and so they aren't very good reservoir, usually. Well, a lot of the work has been done on the Mississippi River Delta, very famous delta, been studied in great detail. And I just want to show you a couple of the results of modern studies that give us clues as to how the delta was deposited in ancient times by studying the modern delta processes now. So here's the delta. Here's the main river, the Mississippi River, comes down. Okay, the Mississippi River comes down like this, like that. And here's the river mouth. And here's one of these distributary bay type deposits where your sand is being deposited. All of this area in here is going to be floodplain muds. That's the material that's formed in these little bays. I shouldn't say floodplain, but I should say little bays. Bays and lagoons and estuaries that all deposit mud. So alongside the river, you've got a lot of mud. Onshore, we call it a floodplain. As you get offshore, it's a more of a bay or lagoon. Now, in order to understand how deltas form, like I said, a lot of work has been done on the modern Mississippi River. So here's the channels, the distributary channels, and the main channel of the river. And that's where your sand's going to be. It's either going to be in the river or it's going to be down here, down there, down there, down there. Now, that's at any one instant in geological time. You can walk down, and that's where you're going to find your sand and your shale, or your mud, at any instant in geological time. This picture happened to be taken on April 10th, 2011. If we go back to a larger time scale that us geologists really like, say thousands of years, we can get an idea of how that delta formed. By the way, if you're following on your computer, I've kind of rearranged these pictures I'm showing now are at the back of this unit, Unit 3. I've just moved them up last night, moved them up closer. So you've got these, but they're not in the same place as I'm on your set of pictures as I'm showing here. Well, okay, so let's outline the delta. Okay, here's your major river, Mississippi River. The delta is really this. That's the delta form. But that did not form all at once. And the using age dating techniques, this time on plant material, doing carbon age dating of plant material, they've been able to work out where and when you had different stages of delta formation. And I know you can't read the letters here and the numbers, but I'll read them off to you. The geology that has been worked out for deposition of this delta goes something like this. About 7,500 years ago, down to about 500,000 years ago, you had your river here, and your first part of the delta formed right out in here. Well, what happens when you deposit that delta sediment is the surface builds up higher and higher along the shoreline. At some point, that delta is depositing so much sediment, and it's very high, so that future flows of the river bringing in sediment can no longer climb up that delta, so it goes around it into the adjacent low area, adjacent to the topographic high area that is your delta. So what happened in this particular case is that after the delta had built up for a while here, to give you this orange subdelta, the direction of sediment transport of the river migrated, and it went over to this area here. That was a low area, so the river started depositing sediment here, and it did that between the time interval 3.5 to 5.5 thousand years. Well, at that time, the delta again became very high here, so you had a migration of the river off to the right, to a low area, and so at about the time interval 4,000 to 2,000 years, this was where the delta was active at that time. So you see, what we're doing is we're building up a delta by deposition in one area, and then another area, and then another area, as the river migrates to these new areas. At, let's see, at 1.3 to 0.9 thousand years, you had this little delta forming. And from about 0.9 thousand years or 900 years to the present, that's where you have and that's the modern day, active day distributary mouth bar of this delta system. So if we were to draw a cross section across here, it would be a mounded type feature with thickness, but the thickness would be variable depending upon how long and in what position you had deposition over that time interval. So Mississippi Delta was deposited over about 7,500 years of time. Determined from your age dating of the plant material, but at different times you had active deposition in some areas and not in others. Well, what would happen, and somebody was asking me this yesterday when I was talking about transgressions and regressions, and somebody asked me, is there anywhere where you've got both going on at the same time? Okay? In other words, what I've been talking about to this point when I talk about changing sea level is up and down. But is there any situation where you're going to have transgression one part of a shoreline and regression or progression in another part? And turns out the Mississippi River Delta is really a good example of that. You have deposition here over the 7,500 year time interval. So you're prograding here, regression, but down in the adjacent areas where you've got shoreline here and over there, over here, you're not getting any sediment at all. All the sediment that's coming down the river is being trapped in the delta. So what happens when you get away far enough away from the delta, you don't have any deposition along the shoreline. And the dominant process there just becomes one of transgression, essentially, because what's happening when you don't get any sediment is that your sea floor subsides. Sea floors around the world are always subsiding to a certain degree. So in this case, if you've got a subsiding shoreline, that's the same as saying that the shoreline's moving landward during that time, or it's transgressive. So, adjacent to the delta where you've got active sedimentation, you have, excuse me, that should be a T. you have transgression over here, and in the main part of the delta, prograding seaward, you get regression. Okay, so that's one of examples where you can get them both occurring at the same time. Now, something like this causes a lot of problems for exploration people, for example, because especially in the old days when we only shot 2D seismic, because you may have you may shoot a single 2D seismic line that goes like, oh, excuse me, let's put one here, goes like that. And you interpret that seismic line and you say, well, this is a marine transgression. Okay, so where's our sand going to be during a marine transgression? It's going to be in the shoreline, like I showed just previously. So you're going to have your sand up here. Suppose you shoot a seismic line here, and what you see is you recognize the delta, so you say, well, you've got regression. Because you get different types of deposits during transgression than during regression, you're apt to make misinterpretations when you shoot, say, 2D seismic lines over an area where this sort of process is going on, which is a lot of areas in the world. So the early on, seismic people who interpreted seismic for their stratigraphic features would make mistakes. They'd make a lot of mistakes. They'd say, well, we've got transgressive sands, so we want to drill our well here, drill the well, and it's all mud, no sand. No, excuse me. There will be sand, it just won't be very aerially extensive. This case here, they'll say, well, there'll be a lot more sand aerially, but individual lobes don't have as much sand. Well, excuse me, I got off track. The sand is going to be moving out in this direction, is what I should have said. Okay, so if you're only shooting one-liners in seismic, you're apt to misplace where you think the sands are, depending on whether you interpret a transgression or a regression. And so that's one of the reasons why we like to shoot 3D seismic now, so that you can get a nice block diagram of your reservoir, so you can get a better idea if you're transgressing or regressing, or if you've got a situation like this, where both are going on at the same time, but in different parts of your shoreline area. Okay? So that's kind of a pitfall that early seismic interpreters, when they were interpreting the stratigraphy from seismic lines, that was a pitfall that they would often make. They would have two-dimensional data that they were trying to interpret three-dimensionally. Or actually, if you include time, geologic time, they were trying to interpret 4 dimensions, okay, 3 space dimensions and 1 time dimension, using two-dimensional data. It doesn't work very well. So, and this is a good example of that. So going back now to the modern day studies on the Mississippi Delta, you can find some areas where at certain times you've had erosion, and then at subsequent times you had deposition in the same place. And here's an example during the interval 1962 to 2004, where measurements were made of the change in volume of the sedimentary body. And so negative numbers mean you had net negative volume, meaning erosion. You've got positive values, meaning deposition. Your volume is changing positively as you deposit sediments. So at this one spot where they had a staging station, between the years 1962 and 74, they had a lot of erosion, a lot of net negative volume or erosion. Between 1974 and 1984, at that same station, they had erosion still, but much less. Now, this line here represents no change in volume over time. So at this staging station, you had this much erosion between 1962 and 74, this amount of erosion during 74 to 84, but then suddenly at that same station, things changed, and during the interval 1984 to 92, you had a net positive volume change, meaning that that same station you started having deposition rather than erosion. And in this interval, 1992 to 2004, you had even more net deposition in that one station. So you see that even at the scale of years, things change locally. From, in this case, where you're eroding sediment off your delta, that's a period of low stand of sea level, where your delta becomes eroded. Then during this phase, though, where you're having net sedimentation, that's a period of transgression, where you're getting space between the sea surface and the sea floor for sediment to be deposited in. So you get net sediment gain. And we can extend this back into geological time. The same sort of thing could occur in an area where you go from erosion to deposition. Everything in geology is cyclic. So somewhere out here, if we were to extend that curve, we would find either erosion or deposition in the future. So that's at a very fine scale, the order of years. And again, you can take this at a larger scale and see how you change either periods of erosion. Say, let's pretend this is about a 10,000 year time span rather than just 30 years. During that 10,000 year period, you might go through a sea level cycle. So I'm going to draw my little sea level curve here. Where would I be now on this sea level curve during this period of time when you're getting erosion? Well, you'd be right on this part of the curve. Where would you be when you're having deposition? At that one spot. You get your deposition up here. Okay, so what I've shown you here now is actually an analog of a longer time interval, say 10,000 years, where you go through a sea level cycle and you change from erosion to deposition during that change in sea level cycle. Whether you have a falling stage of sea level or a rising stage of sea level. I think I'll skip this one and kind of show the same thing. But here now is a close-up picture of this little feature right out here. This modern day delta, or part of the delta. And here it is here, as it was mapped in the year 1937 to the year 2000. And look how that has changed. Yeah.
I have a question. In this process of retrieving and advancing sea levels, how does clay layers get deposited?
The clay represents a quieter water deposition, meaning kind of deeper water. So when would you get that during a sea level cycle? You'd get it on the transgression. The regression, sea level goes down, you get more energy and you erode.
So as the sea level is higher, we get sand deposited, but as well we are assuming there will be some clay in between.
Yes, that's correct. You're going to have sand deposited somewhere. During a high stand of sea level, your sands are transgressive, so most of your sand is on the shoreline. That was what we looked at earlier this morning and late yesterday. In fact, just to clarify that point, I'll go back to that for a minute, to that slide. This morning I started with this, and I drew that little curve where you get a marine regression, so you expose the shoreline.
It's not showing. It's not showing.
Oh, let's see, I got to do this.
Yeah, I remember.
No, I can't see it. So, well, this isn't going to work. I can't see it now, but I drew that sea level curve. A little bit of regression, so you expose the shoreline and you get deposition on the shoreline. Then you get a shale, meaning transgression, deepening the water. Another regression, so you get another shoreline sand. Transgression, giving you another shale. Regression, transgression, regression, transgression, regression. And each, overall, if you look at all of these sands, they're actually migrating in the landward direction, meaning that each change in sea level is more than the preceding one. Okay? That makes sense?
Yeah.
Okay.
Professor.
All right, let's see if I can.
Dr. Slatt. TSE.
Huh?
What does TSE mean in that book?
Oh, TSE. That's a transgressive surface of erosion. So that's at the base of a sequence where you started to have erosion due to very early transgression. I think I mentioned that the other day, but didn't really talk too much about it. I'll talk more about that when we do sequence stratigraphy this afternoon. let's see if I can get back to where I was. Well, let's see, I did something again that I shouldn't have, I guess. How did we fix this yesterday when that happened?
Would you like to duplicate the both?
So I go,
You want to go back to the PowerPoint?
yeah,
So,
yeah. So, I duplicate. Yeah. Okay, I got it.
it's a new Windows 10 feature.
I have a lot of trouble with the old, let alone the new. Okay, so at any rate, guess I was somewhere around here. This is what has happened in one area. What's happening here is you're getting transgression, okay? In 1937, that feature was a fairly large feature of the delta. Okay, it was a large feature of the delta in 1937 when it was mapped. Now, in the year 2000, you see how much of the land area has been lost because it's sinking. Okay, you're not adding sediment, you're not adding new sediment fast enough to build up between the sea surface and the sea floor, so you're getting subsidence, and so you're losing the land, essentially. Or another way to say that is transgression. Okay, so you're transgressing here. Now, here, back in 1937, you had a lot of sand down here. Well, what are you going to have now in the year 2000? You will have sand below that was deposited in 1937, but now you're getting more of these quiet water lagoons and stuff, so you're going to be depositing more mud on top. And in another 10, 20 years, this will be completely submerged, okay, and you'll get finer grain, more mud on top of that, too. So that's an example of transgression and how it operates in this sort of a setting. I'm going to skip these last two, and this is a good time to break for lunch. After lunch, I'll come back and talk about first wave-dominated deltas. Okay, so why don't we break for lunch?